Welcome back, fellow colleagues, part 2. This is intersection of two linked lists. 160. LeetCode. Honestly, this one is marked as easy, but it's a little bit confusing, right? But I think I'm going to show you the most intuitive and simplest solution by far while reaching the same time complexity and space complexity of actually it's not going to be constant space, but that doesn't matter. Okay, it's a pretty good solution. So write a program to find the node at which the intersection of two singly linked lists begin. For example, the following two linked lists begin to intersect at node C1, right? So how do you figure this out, right? So you have A1, A2, C1, C2, C3, they fuse at some point, right? And then they're the same, right? So how do you go about doing this? Right, and we'll take another look here. Boom, boom, boom. Oh, they intersect at 8, right? These intersect at 2. There's no intersection here, right? So there's a couple different cases you have to handle. If two linked lists have no intersection at all, return null. The linked list must retain their original structure after the function returns. So any changes we make, which are kind of hinting here, you can make changes, by the way. Just make sure you revert them. You may assume that there are no cycles anywhere in the entire linked structure. This is also a hint. Wink, wink. But that's not the way we're going to do it, but it's also possible to do it this way, right? And so this is the first way that you can do it. So write a program to find the node at which the intersection of two singly linked lists begins. So the first way, right? First question is, how do you define when two nodes where they intersect, right? Let's just say you create an algorithm, right, where you could where you knew, right? Let's just say you had just A2 and B3, ignore these out here, right? Let's just say you knew the next node, right, was going to be, you knew the next node, they were going to share a node, right? So that seems pretty straightforward, right? Oh, that's the node, right? But how is that different than C2, right? Because what's making these the same is the fact that they intersect here, right? But what's also interesting, right, is you could say, oh no, what's interesting about them, right, is that they both point to C1, right? But if you think about this, if you increment both A2 and B3 to C1, right, it becomes the same. It's just confusing because there's only two arrows here and one arrow there. But both of these nodes would now be pointing to C1, and both of their next nodes would be C2. So how do we know C2 isn't the first intersection? Even if that's the case, how do we know C3 isn't the first intersection, right? So it gets kind of confusing fast, right? Because the picture is good, but it's also a little bit confusing. So how do you do this, right? So ideally, this is a really simple solution, right? So what you can do actually, right, is we can create a dictionary, right? And we can use something that's going to be a more accurate determinator, right, of whether or not two objects are the same, right? And that's going to be memory address. So we'll create a dictionary of memory address to value, right? And the point is, right, the value here doesn't really matter, right? We just want to know, we just want to store every time we go through the first list, we're just going to store its memory address, right? So the idea here is going to loop through first linked list, store every node's memory address to value, right? So now at this point, right, we'll have a dictionary, right, of going through the first linked list of every node's memory address to its value. The value part doesn't matter. We just needed a way to say that we had seen this memory address before, right? And the dictionary is going to allow us to do that in constant time, right? Now we can loop through second linked list, right? If memory address exists in LLDict, we're just going to call it that. That's going to be the dictionary we created earlier, right? Then it means, hey, this is the first node in the second linked list, which is this one, that has the same memory address, or has a memory address that exists in the first dictionary, right? And if it's the first node that's done that, then it's clearly where they intersect, right? And you can see, if you had to generate their entire part of where they intersect, right, you can just create another linked list, right, where every time you can look up a memory address in the first dictionary and it exists, then you can get all of the points where they intersect, right? So if you want, you can get C1, C2, and C3, and you can get that in about 7 lines of code, right? And the thing is, since we're looping through the list, iteratively, right? It's going to be linear iteration through. We're always going to see if this ever goes off, it's going to be the first one, right? So if memory address exists in LLDict, return the node. We found it, right? Otherwise, right, if you iterate through the entire list and you look up every memory address, right? You look up every memory address, so you made a dictionary, right, of 2, 6, 4 to their memory addresses, right? Then you looked up 1, right? Remember, the values don't really matter here. We're talking about memory addresses, right? So you looked at the memory address of this node. It's not in there. You looked at the memory address of this node. It's not in there. Well, if you iterated through the entirety of the second list and the memory address isn't in the first dictionary, then they don't intersect at all, right? Because ideally, well, not even ideally, strictly speaking, if they intersected, eventually there should be a node that shares the same memory address as the node in the first linked list, right? Because they would match up. And so if that's not the case, if we never ever ran into a node, right, that shared a memory address with the same one in the first linked list dictionary, then we're just going to return none. There's no intersection, right? The promise is here, return, if there's no intersection at all, return none, null. So let's just follow the code. Now we have the scaffold and create a dictionary of memory address to values. Let's just call it head a dict, right? And we'll just call it this. That's going to be our dictionary. We said loop through the first linked list. Okay, so while head a does not equal none, right? Store every node's, oops, having some keyboard troubles. Store every node's memory address. Okay, well, let's just do that, right? We'll just say head a sub dict sub, and this is how you get the, I guess, the address of memory address of an object in Python. You can just say ID here, and it's not exactly the memory address, but it's a unique number representing the object, right? And so you're just going to say, or you're just going to store the ID of head A, and here we're just storing it with the mapping to value, right? Even though we don't really care what we map it to because we're never going to retrieve this value, we just need to know that it exists, right? We're just going to say head a dot val. So that's all we need to do there, right? And of course we have to head a is going to be equal to head a dot next, so we don't end up in an infinite loop. And then we're going to do the same thing for here. While head b does not equal none, we're just going to iterate through the second linked list, right? If memory address exists in LLDict, well, we called it head a dict, so we're going to say, hey, if the ID of wherever I am in head b, right, is in head a sub dict, then return the node. We found it, right? This is it. Return head b, right? And then we're going to do one more thing, right? Obviously, we don't want to end up in an infinite loop in the second one either, right? And then that's it. Now, if we run this, we should get intersected at 8. First time doing this problem, by the way, easy clap. And so we get this answer here. So pretty good, right? So what's the time complexity, right? Well, it's going to be O of m plus n. Why? Because we have to iterate through the first list to create the dictionary. We have to iterate through the second linked list to look up the values to see if an intersection exists, right? Otherwise, we return none, right? Well, what's the space complexity, right? Well, if you wanted to really optimize this, right, you could iterate through the first list, iterate through the second list, get both of their lengths, right? And then you'd know, okay, which list is smaller, right? And then you could store only the dictionary of the smallest linked list, right? That way it'd be much simpler to know. You'd be storing a lot less space, right? But it really depends if you want to do the optimization. Now you have to loop through the array 2 more times, which kind of sucks. I mean, loop through the linked list 2 more times. But for simplicity's sake, the time complexity is just going to be O of m, or the minimum of O of m plus n. I mean, the minimum of m or n if you wanted to take the smallest list to store it, or for simplicity's sake, just space complexity of O of m. So this is intersection of 2 linked lists 160.